SwayamPrabha. Digital India. Educated India.
Welcome to the class of Intelligent Product Design. This is the penultimate lecture, and in which we will do another case study of a very interesting intelligent product, which is named as NSVS, that is Nirasara Swamsasito Vaidsala in Sanskrit, and in English you can translate it as Autonomous Aquatic Observatory. This was a joint project carried out between the Woodsoul Institute and IIT Kanpur, and this project was sponsored by Department of Science and Technology and Indo-US Science and Technology Forum. So, in this initiative, we had actually tried to develop an autonomous system which can be stationed on a river, and this system can continuously acquire data from the river water and then report it directly online, such that people will be able to know that whether there is any pollution that is taking place in the river. Now, such a system first of all is very important to save the aquatic ecology of our country, because as you know very well that all these rivers are the lifelines for millions and billions of people of our country. So, hence the rivers must have good quality of water flow in it. Now, there are already provisions of human based supervisions, but they are very much resource constrained and they cannot do such supervisions continuously all the time. Whereas, what we need is a continuous supervision of the river water quality, which only an autonomous system can do. So, this was the great objective of this particular project, and through this case study, we will be able to see what are the type of sensors, what is the type of the structure that could hold it, how the communication had been established, how the very important issue of supplying power to the system so that it remains self-powered had been resolved. So, all these things becomes part of a typical intelligent product design. That is why we have taken these as our further case study. So, a bit of background, that in this project we propose to design and develop low cost multi-parameter water quality platforms that would consist of several in-house developed sensors and a very interesting auto sampling capability for durable and reliable real-time monitoring of the river water quality. So, the salient features that I will discuss is that the in-house developed array of water quality sensors and the auto sampler, design and development of stable autonomous stationary platform which will not perturb much even if there is a change of flow condition, let us say from the dry season to the rainy season, even if there is a storm it should not topple. So, these are all design challenges. Wireless signal transmission system between the robots and the platform and the local workstation. So, the data should come from the autonomous robot to a platform which is on the shoreline, and from there it should go to the workstation which is quite far away, placed somewhere inside the institute. Then number 4, that a versatile energy harvesting system in modular form, so that if one does not work the other would work. So, in that kind of a modular form for extracting energy from two sources, that is vortex induced vibration and the other one is from the solar energy. Real time data transmission I have already talked about, and finally the design, development and maintenance of a web portal where all these data would be collected and displayed for the use of the people and the specialists in the field. Now, I am coming to one of the miniaturized in situ sensor which was developed in Woodsole Institute of USA. This is called channelized optical system or CHANOS. Now, this CHANOS system, it has in situ high resolution spectrophotometric measurements of dissolved inorganic carbon. So, spectrophotometric measurement is something where you actually collect the light that is sort of reflected back from the water, and from the spectroscopic study of it we try to see that whether there is inorganic carbon dissolved in the water, because if there is a high degree of dissolved inorganic carbon, that would mean there is a high degree of presence of decayed animal and plant parts, pollutants, organic nature, etc. So, for that point of view, CHANOS 2 had been actually designed and developed by the Woodsole Institute and sent to us, and also we had sort of customized it so that it can not only detect the DIC, but metals. As you know that there are many polluting industries such as the tannery, where the metallic pollution is possible. So, metals like copper, cadmium, etc., that also the spectrophotometer should be able to detect. So, the feature is that the measurement is taken 1 in every second. So, it is a 1 Hz measurement, in situ calibration using reference materials, and the precision of DIC should be 0.1%. So, that was quite a big challenge for the system. This is how a CHANOS system typically look like, and you can see both the sensor bay here, that is the sensor bay where the spectrophotometer is installed, and the electronic housing, power, PCBs, etc. So, this entire sensor is of very small size, 27 by 9 by 41 centimeter, in comparison to the enormously complex task that it is doing, and its weight is about 5 kg in air, and the electronic housing is also there, about 52 centimeter length and weight is about 12 kg. Then there are reagent box which weight is about 6 kg in air. So, that is the system, that is one of the prominent system of this particular setup. Now, other than that, we have also had the additional sensors, because it is a multi-sensor system. So, these other sensors are first of all a miniature oxygen sensor, that is the dissolved oxygen sensor, or we can call it as a DO sensor. So, this is a dissolved oxygen sensor. So, dissolved oxygen sensor will actually tell us that what is the level of oxygen available in the water. Why? Because if there are lot of biological organisms present, or if there are some chemical reactions happening, then they must be consuming oxygen, oxidation would happen, and hence the free oxygen presence will actually come down. So, the presence of oxygen, in other words, tells us that whether the water is healthy, potable or not. So, this is why a miniature oxygen sensor is very important, and its response time need not be so fast as the spectrophotometer, but response time up to 10-second level is good enough for us. Precision should be better than 0.1%, and the size is very small, like 1 centimeter cube. Power, most importantly, is less than 0.5 watt. So, it is a very low power consuming device. Now, the next in the line is actually conductivity or salinity sensor. This is a micro electromechanical system. So, it is a MEMS sensor, and this sensor has to actually find out that the presence of the salinity or sodium chloride or the conductivity because of so many reasons like the presence of metals itself can increase the conductivity. The response time here is less than 2 seconds, precision better than 0.1 PSU in terms of salinity, and size wise also it is small, 1 cm by 2 cm by 0.1 cm, but the power most importantly is equally low, less than 0.5 watt. We also then need pH sensor, because these pH sensors can actually sense the acidity of the water. So, if there is a highly acidic water, that would also indicate that there is a high degree of pollution happening in the system. The pH value's response time is about 5 seconds, precision is better than 0.1 pH, and the unit size is 1.2 cm by 15 centimeter. Again, the power most importantly is less than 0.5 watt. In each and every case, the power requirement should be as low as possible, because we have to generate power on board. So, now there is a water sampler that is also required. Why? Because you see, we are only having 4 onboard sensors, the spectrophotometer, and then the DIC, then the dissolved oxygen sensor, and the conductivity sensor. But there are so many other water parameters that you need to know. So, how do we know it, and how do we know particularly how it is varying with respect to time? So, here again Utsol Institute had set a standard for us by helping us send us that a discrete water sampler. So, what does this water sampler, which is a automated water sampler, that does? So, first of all, it has to be a low cost, low volume, and a time series monitoring system. And what it does is that at certain specified times, or based on the instruction that has been sent from the shoreline or from the workstation, it actually collects a little sample of water. So, that it does through the capillary tubing based sample storage system, and then this stores it, and these are later on, after a month or so, they are all retrieved, and each one of these storage places, they are actually checked through the available multi parameter sensing system in our institute, and from there we would be able to know not only about those 4 parameters, but many other parameters to completely quantify our system. In fact, we also had another point in our mind, that we had some data that we are taking on the site, and some data that we are actually keeping through water sampler in the laboratory. If we can develop a mapping between them with the help of a neural network, then later on we do not need all these laboratory testing, but simply that trained network can tell us what are the estimated values of each of the parameters. That was also another direction of thought for which we had chosen this particular auto sampler system. And then this system has its own, of course, battery power, and pre-filter also is added to it, so that it does not get choked too early. Now, we also wanted to reconfigure the project so that we can collect the water and use E. coli analysis, and also instead of external power, we will try to generate our own power in the system. So, based on our in-house sort of parameters, we kept the preliminary power consumption level to be less than 2 watt while sampling, and 0.5 watt at rest. Communication protocol, we thought of using RS-232, and then the air intake lines to surface for sample purging and storage. All these things are designed. Ideal sampler body, packaging which should be waterproof, packaging should be a mixture of aluminum and plastic to make it as lightweight as possible. No chemical storage is required, but the design is extendable for chemical storage and injection in future. Now, then the most important thing is, of course, the platform design, which is going to house the sensors. So, I will tell you a few things about the platform design. So, the aim here is to develop autonomous river surveillance and monitoring platform for local water quality monitoring, and measurement of flow parameters. So, you can see this is a kind of a product that was available in the market YSI 6952, against whom we can actually sort of calibrate and we can sort of benchmark our system. Now, we wanted to build a new buoy first of all, which should be stable as a platform, then housing several in-house developed sensors and auto sampler, wireless signal transmission system inside, versatile energy harvesting system for vortex induced vibration as well as solar energy, and a web portal as I told you earlier. So, this is the first conceptual design of the system, where you can see clearly a few things, not all the things are visible from outside, that this has a structure which maybe will go up to this point maximum under the water. Okay. Now, you have a float here, so that actually helps the entire structure to sort of remain over the water as much as possible. We also have this particular system here which can be used for anchoring and also for collecting water samples. And then we have somewhere here we have the housing for all the sensors, and the top part is kept for the power generation, particularly the solar power generation system. So, that is the overall system that we had in our mind, and the design objectives were that it has to be a robust system, it should be stable in high wind and river current, lightweight. As I told you, arrangement included for attachment of mooring chains, that is in the bottom, enclosure space effective enough to house all the sensors properly, solar panels and safety considerations. So, for the buoyancy part, the forces that are considered are the buoyancy force and force from other component or devices, weight and the damping force. Now, let us look at the conceptual model, how it would look, and the corresponding design features. That this system must be easy to deploy, that is one very important point. It should not be so heavy that it would be difficult for people to deploy it in water for the first place. Then it must be able to support sensors like DIC and then of course CU, CD etc., the sensor for the metals, then DO oxygen sensor, salinity sensor or conductivity sensor and pH sensor. And then inside the hull we will be having all the monitoring equipment, that is something that I already told you. And the hull we initially thought would be made of polyethylene and inert foam core. And initial choice of material for the upper structure was mild steel, L-shaped channel and aluminum sheets. And then the hull shape is something that we had to do as hydrodynamic as possible, and there has to be a beacon installed at the top. So, these are some of the design specifications. Once you qualitatively understand the features, then the specifications, for example, the hull weight about 240 kg, hull would displace about 280 kg of water, hull diameter is also fixed something like 1.25 meter, hull height 0.5 meter, total height, that means this is the top part and including the part that is submerged, total height is about 1.75 meter. And then the solar panels that are to be installed on the system. So, first important point here is the stability calculations. Okay. So, the stability calculation is required for what? That if there is a storm that is coming, this whole thing should not be actually toppling. So, in order to do that, first of all we have to calculate the two things in it, that is the buoyancy center and the center of gravity. Okay. And once we actually calculate these two things, then we can calculate the GM, and if the GM is positive, right, like in this particular case considering all the geometry of the system, the GM would come out to be about 185 millimeter and it is positive, then the system is stable. Another thing that we also have to see is that suppose if I sort of a little bit vibrate the system, how long does it this oscillation continue, how long does it take to come back to a normal static position, and that also has to be as low as possible. In this case it came out to be about 2 seconds. So, here is the buoyancy analysis that we have carried out, and you can see that how we have first of all figured out the forces and the maximum force that is possible in the system, and then corresponding to that force what is the deformation that is coming up in the system, and of course, the stability margin that I already told you. So, one of the important thing is that as a structural material based on the forces, we had decided to use linear low density polyethylene, and then also we had to select material such that there are higher environmental and stress cracking resistance, and also high toughness and tensile strength, and has minimal impact on the environment. So, this is the first prototype that has been developed. So, you can see that in this prototype one by one you can see that how different systems are. So, once that float goes away, you can see the system inside where the sensors and their connectors etc., the filters and all these things are kept. So, you can now see everything is revealed now. Okay. So, that is the sort of a dissociation, and then you can again assemble the system. So, out of the choice of materials, so we could choose either fiber reinforced plastic or high density polyethylene or polyurethane foam. So, we have chosen a reasonable balance of these three materials along with provision for mooring and lifting. Okay. So, that of course has to be done at the far below bottom end of the system. And then we also kept another interesting thing, that not only the vortex induced vibrator, but also we had kept the vertical axis wind turbine provision, so that even from wind it can generate energy. And each one of these systems were actually modular in nature. So, you can see here that a lead screw is threaded inside the structure. So, you can see the movement of the system here, and so that you can generate a linear motion in the system, and that will help in terms of lifting up water samples. Then sensor and auto samplers are attached to the holding plate. Holding plate also has a threaded rod on the middle plane, and the middle plate is fastened to the polyethylene buoy. So, this is a video animation that actually shows how the whole system would actually move. Now, the final specifications of the system weight came out to be approximately 180 kg, the hull displays about 280 kg. So, there is a good bit of sort of a stability margin in the system. Hull diameter I already told you about 1.25 meter, that is coming from the requirement of the sensors. System height also from the same requirement. Water line depth from the keel comes out to be 0.772 meter, which is okay for such a system, and the center of buoyancy and center of gravity needed to be obtained for the system, and then the metacentric height, which actually tells us the GM, which actually tells us that whether the system, even if you topple it a little bit, whether the system is going to be stable or not. Now, I told you that there are other similar systems that has been developed by people. So, you need to always sort of benchmark your product. That will also show us that where to grow. Now, such a thing is generally done with the help of house of quality, which you might have gone through in any design course and on design principles, and the baseline here is actually quality function deployment or QFD. So, using QFD you can actually fill up this house of quality, where on your left side you have all the customer requirements, and here the customer rating is actually established by giving scores against each one of these parameters, and here it is actually showing its correlationship with the manufacturing, so that you know how much your decision is entangled with the manufacturing decision. Now, one important thing is the selection of the wireless technology, because it has to be of long range, because from the place where the robot is kept till this shoreline, it must be able to send the signal, and it should be low power, low cost, works in a delicensed environment so that it would be cheaper, and it should be open source based, ecosystem should be there. So, there are lot of possibilities, and what we had chosen is a WLAN system, that is the wireless local area network system, such that it follows this 802.11h and 802.11p. So, following that, the wireless sensor technology has to be done. So, here at this stage we have checked with respect to different such technologies in as a low cost device, and also it has to be open platform device, as I told you. So, their solutions were like Sigfox, LoRaWAN, Ingenu, Weightless W, Weightless N, Weightless P and Dash 7. So many systems we have considered, their ranges we have noted it down, and then finally we could see that one of them, like the LoRaWAN, is very much suitable for our particular design. So, now selection of wireless technology, LP1 versus the cellular part, and LP1 was preferred because low power consumption, and most LP1 technologies work in unlicensed band, and then it offers more open ecosystem. That is why we had chosen LP1, and here is the LoRa, a little bit of comparison. LoRa has the most open ecosystem. Sigfox is not very power efficient, LoRa is power efficient, and Ingenu, particularly out of this group, has been discovered because it has been discarded, for it was meant for use cases with higher data rate requirements. I will now show you the energy absorption part of it. So, this is a solar energy harvesting part. The detail of the panel and everything is given here. So, there is a bit of an animation, you would be able to see that how this entire floating platform is moving in order to keep all its solar panels to be energized. And then the other sensory system we have used is called vortex induced vibration, or VIV. So, in the VIV what happens, this entire body works like a bluff body, and hence the water coming from the upstream actually creates the vortices on two sides, and these vortices can actually vary the lift force. So, if you have such a system, one or two or four of them actually hanging from the leg, then they start to vibrate, and as they start to vibrate, then they would be able to actually generate energy into the system. So, for this design we need to know the maximum energy output corresponding to maximum amplitude of the oscillation, and what is the lock-in frequency, that is what is the resonating frequency of the system, so that there these lock-in can happen, and the amplitude of order d, the diameter of cylinder at least we are expecting for such a system. Remarkably, we have seen that our system works for a very low water speed, something like 0.5 meter per second, which generally the systems would not do. Now, this is the first series of stability test of the system, and this entire thing had been done at a place which is little bit away from a river, but quite adjacent to the river inside Kanpur Zoo. And then we carried out dynamic stability analysis, real time position determination, and we entered the raw data for future reference. So, this is when we were actually testing the vortex induced vibration system. You can see that as the ball is moving, initially there is no change, okay, but if you apply a vortex like we have done it here, the vortex kind of shredding system, the bluff body. So, then what happens? So, you can see that the flow of water is taking place. and you can see that there is a gentle, very gentle oscillation that has already started to the system, swaying. Okay. So, that can be extracted in terms of the energy. Now, this is something when the entire buoy had been tested, as I told you, the initial testing phase in a little bit of still water, and then we further used it in terms of collecting data from the river Ganges. So, this entire product thus tells us that how to develop a completely intelligent, autonomous aquatic observatory system, which is can become very easily the lifeline for the people of India. Thank you.